thing. All right, sorry everyone, let's start. All right, I believe you can see the file I'm sharing. Just give a thumbs up if you do. Just guy. Okay, right. So as I said, in today's lesson, I'll be covering the CPU OS simulator at full length. Um, so follow through, open your simulators alongside because we'll be doing some practical moves later. This slide is just short and it's going to show you what some of the things you see on the simulator that mostly confuse you mean before we delve into it. So let's start with that. So by the end of the lesson, we should be able to identify the key concepts of the central processing unit operating system simulator interface, explain the difference between logical address and physical address. The logical address and physical address are two parameters that you often see, but you may not know exactly what they are. So when you check the columns in your CPU OS simulator, where it says instructions, you realize that it has LADD at the top, one of the columns, and it has PADD. Those two stand for logical address and physical address, respectively. Then, as we go, we also distinguish between memory operations and stack operations. Then, we will trace the execution of instructions step by step to observe register changes. So, it is my hope that by the end of this lesson, I will be able to pass on everything that you will need to know, at least for the beginner in the central processing unit operating system simulator. The simulator's endpoint is just to make you understand how the CPU runs on an internal level, like down to its cycles, very low. So for that reason, this is why we are using these simulators. So it's not as if the simulation thing is for exam. And I do not know how exactly the lectures exam will be. But as far as I'm concerned, this is just to give you a deeper understanding of how the central processing unit works with information and then brings out results. Why use a simulator? So now, a simulator is a software tool mimicking a real processor without hardware. So it says the uses of it is that it allows us to work and understand the central processing units in safety. This means we will be able to just fool around with the CPU and understand the true experimenting, because in the process we'll be making some mistakes, but without the risk of actually damaging the real CPU. And also visibility, it helps us see things that are inside the CPU that we normally shouldn't see. So it helps us see how those things. So it says like it sees inside registers and memory, unlike sealed CPUs. And then realism, the models real concepts, that's the base registers, the stacks, unlike the little man computer. So the little man computer is so human that it does away with a lot of the things that the central processing unit offers. And then for that reason, it does not begin to even tell you how the CPU actually works. Maybe it does about 5% of the job, but the CPU simulator, if you follow it closely, you are just going to understand most of how the central processing unit works, at least on the software level and hardware as well. All right, so here are some key vocabulary that you should look out for as we proceed in the lesson. There is the register. So the register is the central processing unit registers. They are fast storage for current data or instructions. Registers are fast storage for current data or instructions. Then we have the address, a unique number that identifies a specific location in memory where data is stored. So you see, we've been mentioning things like memory address, instruction address, etc., etc. So the addresses are numbers that are holding or are telling us where exactly something is happening or where something is held. So that's what the address is. Remember that the register is one of the storage spaces, but think of the register as a very temporal one. It doesn't store things in the long term, just in the short term, but it allows the machine to work fast. So when it comes to speed, the register is able to work faster. But when it comes to containment or storage capacity, RAMs have higher storage capacity as compared to registers. So registers, you can think of them as fast thinkers. So they are able to remember things fast. However, the RAM is able to remember things for long. So these are two ways you can look at the difference between these two storage spaces. Registers are fast reminders, or fast, should I say rememberers? I don't know. And then the RAM is what do we call it? A long term, someone who remembers things in the long term. Yeah, I think. All right, to proceed. So then there is a pointer. A pointer holds the address of another memory location. Sometimes it could be the address of the next instruction to be executed. Sometimes it could be the address on the stack, where the stack is currently. So we'll be looking at those ones too as we go by. And then there is a stack. A stack is a last in, first out data structure used for temporary storage, often during function calls. So if you remember the stack, it was mentioned by Professor Solomon in his previous lessons in the last semester. He mentioned that it is a way that RAM holds data. And then it does this by piling the data. You can think of it as stacking up the data in like plates, as you can see here, a stack of plates. So one data goes in, another one comes on top, etc., to this side. If you study the structure carefully, you see the first plate that you would have put in this stack falls at the bottom, right? And then the one that follows is on top of it, and the one that follows is above it, all the way to the very last place that you place on it. Therefore, the last place becomes what you can take out first. So it says the last in becomes the first out. So we say the architecture for a stack RAM stack storage is last in, first out, implying that the last data piece that you put inside becomes the first one that you retrieve from it. And also there are two things that you do with a stack. Adding data to it is called pushing. So when you push, it means so be ship. And then when you pop, it means free, so you're taking away. Let's use these simple things so that we can record these things easily, and then we wow the lecturer in the next meeting. All right. The central processing unit registers panel. So now when you look inside your central processing unit operating system simulator, I hope you are looking at it. Please give me a thumbs up if you have it open, because I'm not going to display it right now, but I'm just using the slides to show you exactly what I'm talking about. Okay, one person says he is using it. Auntie Mona, Auntie Mariam, Mr. Jed, everyone else in the meeting, please, are you also having your operating system simulator open right now? Okay, all right. One person stamp is up, so I'll just assume he's the only one. The rest of you, we beg you, join us one. All right, so now we start with the very first one. We're very familiar with the program counter. Program counter holds the address of the next instruction to be executed. So what this means is that if I am standing on a line, for example, I'm on line 0, the program counter will be holding the address of the next line, which is line 1. Its job is to lead the computer in a linear path so that it does not deviate away from instructions. It will not skip one instruction and go to another. So it increments sequentially. It follows a particular sequence to do the increments. Sometimes it can do it by increasing by 1, plus 1, plus 1, plus 1. So it means from instruction 1, go to instruction 2, go to 3. Sometimes it can do it in intervals of 6. So from 6, go to 12. From 12, go to blah, blah. Sometimes it can do it in intervals of 7. From 7, it maybe starts at 0. It goes to 6. That's a 7 jumps, right? And then it starts from 7, it proceeds all the way to, let me see, 13. So what this means is that it counts 7 as one of its place to stand, and then it proceeds all the way to 13. So 7 is 1. Yes, Madam Monica.
Please, are you sharing your screen?
Yes, please, I am sharing my screen. Please, do you see my screen?
Oh, I can't see your screen.
Ah,
I can
mobile
see your
is
screen.
mobile game. I think your network is doing me hour, so you need to find
And
a way
please,
around.
what screen are you posting? Because he's mentioning numbers, but I'm only seeing written stuff.
Ah, okay, I understand. So, Mona,
So
right?
so
I
you
am saying that.
log out, then come in again.
Oh no, don't log out, don't log out. Wait, hold on. I was saying that currently I am displaying the slides. I am not switching to the simulator. So you should open your simulator and then match what I am saying right now to the parameters over there so that you can learn in the process. Because if I just start pointing out things, yes, it's going to be good. So now I'm using these texts here to explain that. And when I'm done, we will go straight into the simulator and we will start doing some actual practical there, okay? So Mona, just open your simulator and then follow what I'm saying. So I'll take what I said again. The program counter written as PC in the CPU registers panel at the top right corner or top middle section of your CPU or simulator. What it does is it holds the address of the next instruction. Now, I was saying that let's assume what you see on this page right now, what you see over here is currently a set of instructions that are supposed to be executed. Now, when the first instruction is being executed, let's say the run command is the first execution. As it is being executed, the program counter is going to be holding the address of the next instruction, which is step, so that the computer knows that once I'm done with run, I move to step. It tries to maintain a sequential flow of the instructions executed so that we do not mess up the order, else the computer will end up running instructions at random, and then in the process of doing that, it will mess up your whole code. So then the job of the program counter is allow for a linear flow, a linear sequence of program instruction execution. Keep that in mind. It can do this in fixed sequences. It can do this in increments of one. So by going from 0 to 1, from 1 to 2, from 2 to 3. Sometimes it can do it by starting from 0, jumping to 7, continuing from 7 to 13, from 13 all the way to, what do we call it, 19. So then counting the starting point, it adds other jumps to it so that it makes 7, 7, 7, 7. So from 0, 1, 2, 3, 4, 5, 6, that's 7 jumps. Then from 6, 7, 8, 9, 10, 11, that is another 7 jumps. And then from 11, 12, 13, 14, 15, 16, all the way. So in increments of 7, 7, 7. That way it maintains the flow of the program, preventing it from running into like a random execution sequence. Then we come to the next one, BR. The BR is the base register. Now you will set your base register yourself, but by default it is set to 0. Now inside the central processing unit, if you remember the little man computer we were using, it always started execution from 0. However, in real life, the RAM, the central processing unit doesn't work like that. What it actually does is it uses the base register to draw a line, like a boundary, to tell the computer that always start execution from this side. If the user explicitly defines his base register, there is no way the computer will be storing an instruction in an address that the user is also storing an input or output in. So if you recall our first lesson on the little man computer, some of you were running into some problems where when we stored a value in 5, register 5, or sorry, mailbox 5, your problem was that if you retrieve the data there, it tends to give you something else. And this implied one thing. The lines of code that we had, there were 5 of them. This means the fifth instruction was already being stored in register 5. And that's the problem the little man computer has. Because it always starts from 0, it will already be storing your instructions 0, 1, 2, 3, 4, 5, according to the numbers in the memory as well. So this means that if you are going to use the memory location 5 for an addition or something, it is already holding an instruction that you entered previously. But the base register here prevents that from happening. It tells the program to always start from where you have assigned it to start. So if you give it 100, the program will always start execution from 100. So that's the base register. Keep that in mind. Then we have the stack pointer. The stack pointer tracks the top of the stack. Now, do you recall the stack that we mentioned a few slides back? And I mentioned that the stack is a separate RAM storage, and it is used to hold data. And you do this by pushing and then popping. Pushing means you add, popping means you remove. Whenever we put values in the stack pointer changes its value, its number, indicating that something has been added to me. It always points to the top of the stack, okay? So pointing to the top of the stack, assume these instructions here are my stack. Currently, the stack pointer will be on this very line here. So if this very line is line number 200, the stack pointer is going to read line number 200. If I add another instruction to it, this means I have pushed one on it, right? It's going to force the stack to increase by the size of the instruction. So then if I add, so let's say I want to 200 and I add a word is 16 bits, right? That's 2 bytes. That is exactly 2 bytes. It's going to increase from 200 to 202. It will display in the stack pointer. This means that you have updated the stack. Remember, the stack is a storage means. It's just the RAM, but a different RAM, mostly used to store high-level data or storing values that the user has explicitly stated should go in the stack. Keep that in mind. So the stack pointer is always tracking what is on top of the stack, always tracking what's on top of the stack. And then we have the status register. It stores flags. It tells you what was the result of an operation, how it was. Was it negative? Was it positive? Was it zero? So the status register, the status register stores the state of the executed commands at the end of it all. So the results of arithmetics that we do, they always affect their status register, or at least sometimes they do. If the value is negative, you realize that the status register has 3 indications. So can you see 3 indications? There is an N, there is a Z, and then what else is there? If you are looking at it, what else is there? There is an N, there is a Z. What else is there?
OV.
OV, thank you. So then it means you really are looking. So OV, if you will remember what we learned about signed magnitude back in semester 1, level 100, you remember overflows. When you do operations on binary numbers or when you do operations in different number systems, sometimes there happens to be an overflow. So maybe you are working within 5 bits, but the answer you get is a 6-bit answer. What this means is that the answer exceeds the size of the storage. Therefore, the last value overflows. So the OV records overflow. It means the value that you're trying to store here is exceeding the storage space. Therefore, some of it has been carried on to the next. So then the status register is used to talk about the state of the, what do we call it? Arithmetic operations that you did, their results. Were they negative? Were they positive? Were they larger than the storage space? If they are negative, it is registered as N and is flagged in the status register as 1. This means I recorded 1 states. That's the negative state. If they were negative and an overflow as well, it is going to record take N and also it is going to take OV, implying that I recorded 2 different ones. So then the status register is going to write a 2, implying that there were 2 different states that I read on the value that was given. Let's move on. The memory and controls. We start with the instruction memory. So you see on the top left corner where it says the instructions, blah, blah, where your codes will go later, will come there. That's where it's called the instruction memory, whatever. Now, that's where your codes will live. Now, under that, when you go to the bottom, far on the bottom left corner, there are the program lists there. The program list is a little next to what you have there, where it says add program or new program, whatever it says there. Over there, you see some buttons like run, control buttons like step, control buttons like resets. These 3 here, their functions are simple. Whenever you have codes running, we know what it does. It runs the code and then executes the instructions so that the user can see the outputs or whatever input that they fed the program earlier on. Simple. However, the step command is basically run, but it executes 1 line at a time. And it says it's best for learning so that we can easily track what happens at every step. So we'll be using the step a lot more than the run. And then there is the reset. The reset just makes the code start fresh. the initial instruction again. So it always resets the code to start over. So we'll be using these ones. We are just learning about the interface before we delve into it so that it will be very easy for you to go through. Before I proceed, are there any questions? See, just any question concerning what I have just talked about. And don't worry, if there are questions about things to come in the future, they will be covered in the future. Okay? Just relax. But if you have any question pertaining to this, let me know. If not, just give me a thumbs up and then I proceed. Okay, two people just gave thumbs up. So the rest of you, I assume you are either tired, sleeping, or maybe you know it's past or you don't really care. Okay, let's proceed. Now, logical address versus the physical address. So when you check your memory instruction on the left-hand side, top column, where later we are going to write our codes are going to store, our instructions are going to be stored later. It has LAD, one column, and it has BR, one column. And it also has T on another column. And then it also has some other distance. We'll come to them later. It also has physical good PR, it has base, BR. The T stands for time, BR stands for base, as you are seeing it here. The LR stands for the logical address, and then the PR stands for the physical address. What's the difference between these two addresses? Go back to the little man computer. Whenever a program is being executed, we assign addresses to it: 00, 01, 02, 03, 04, 05, 06, etc., etc. These addresses are known as the logical address. What it means is that you want, or this is what you think the program should run like. So you think the program should run by going to instruction 1, instruction 2, instruction 3, instruction 4. So the computer sees that, okay, this is what the user is thinking. So this is the sequence that the user wants me to follow. Putting that logical address aside, remember, it is how we suppose the program should flow and how the computer makes you also think that the program is flowing. However, that is just the logical address. Aside the logical address, there is another address known as the physical address. The job of this physical address is it makes sure that the computer is not mixing up data and storing them at random places, making sure that data is stored in a proper sequence so that we will not face the same problem we had in a little man computer when we started, where we were storing data in a region where instruction was already being held. So the computer was holding instruction inside the data spaces, but we didn't know. So then we use the logical address and the physical address to differentiate these things. The logical address, remember, it is what you will give the computer in your addressing, or what the computer starts with by default in its addressing. So the computer can start with a 0, then it follows a sequence. Maybe I start with memory register 0, let me move to memory register 6, let me move to 12, let me move to 18, etc., etc. That's the logical address. The physical address is a combination of the base register as well as the program counter. Keep that in mind, though. The base register and then the program counter. Remember that the program counter always tells us the next instruction to be executed, and the base register tells us where to start. So this means that the base register is the starting point, 100. The program counter sees or reads a line, maybe line 1. The physical address is going to be 101, implying that the base bottom or the bottom line that we are not supposed to go beneath is 100. Program counter is telling me to start at 1. So I am just going to start from 100 and jump to 1. So from 100 to 1, where do we go to? It's 101, right? That becomes the physical address. So if your logical address is 2, then it means the program counter will say we are moving on to 2. The physical address is going to be the base register plus the logical address. This means we do not go below 100. That's our base. But since we are executing the instruction held at 2, we are going to start from 100 and 2. In other words, 100 plus 2. If we're going to start at 100, proceed to 2, 102. That becomes the physical address. So the physical address is the actual address that the computer uses to hold the information, whereas the logical address is what the user thinks that the computer uses. So logical address goes more into the flow of the program in the user's eyes, whereas the physical address is how the computer actually stores it inside. So it means you are working with a computer, but it is also thinking in a different way. Despite the fact that we are looking at its central processing unit, it is still thinking differently, even as we see it in real time. So they want you to see the difference between how the user input affects the addressing and how the computer actually considers the address and uses it. Is that clear?
Yes.
I assume that is clear. If it's not clear, it's clear.
So,
We proceed.
Prince,
Yes, sir.
Can
please,
you
can,
go
uh,
over
can you
again?
can you take it again? All right.
Yeah, why want to know? Okay, I'll go over it again. I was saying, inside your computer, let me use the little man computer first. Then I will use the simulator too. Since questions are coming, we can start popping things up. All right. Now, everyone, look closely. You see, when we write instructions here, for example, inputs, and then we assign it a particular address, 00. And then we move on, and then we do same for another instruction, say outputs, and then we assign it an address 01. What you are seeing assigned here are what we call the logical addresses. Keep that in mind. This means that the computer should run according to these lines, starting from line 1, following up to line 2, the logical address. However, what the computer should actually do is this. Even though you have written these two things here, you as a user can later come back and say, on line 3, I have the instruction, maybe add, maybe. So let me put two more inputs. So I had input here, right? And let's take another input. Good. The P key on my keyboard is not working. Okay, my keyboard got fried recently by carrots. So the P key is not working. Let me use on screen. Good. All right. So now what this means is I take first input, I take second input, right? We can decide to store the first input somewhere, and that is where we can see where the true problems lie. So now if I store the first input, I can say maybe store first input in memory address, something like 01. And then I come to second input and blah, blah, and then I proceed. Now there is a problem. You see, this level here is already 1. And then I am storing a value inside the very same address that is holding the instruction. This gives us a problem. So when we're running our codes, we realize that some of us, because the numbers we were using over here were coinciding with the very same numbers we were using here, it was giving us problem with our outputs, implying that the same place where instructions were held were the same place we were telling the computer to keep data. So the computer was now torn between storing the instruction and storing the data. And this is why when we performed some of the operations, the answers were still not coming out. These things you are seeing here are called the logical address. They are the flow, or they are the way the computer should flow from instruction 1 to instruction 2, the logical address. So then to the user, it looks like the computer should start from instruction 00 in register 00 and flow to 01, continue to 02, continue to 03. Is that all right? That's how it looks like it should happen. But because we can see problems like this one, where the user stores data in a region where instruction is already being held, the computer does not do the same thing. Instead of just going ahead to store user data in random RAM boxes, it sets a bottom line. So the computer, if we are using the other interface, we give something which is called the base register, telling the computer that do not start from anywhere earlier than this register. So for example, if I set my base register to something like 100, it tells the computer that everything at the back of 100 do not start before you get to 100. So if I want to execute any instruction, no matter what instruction I give you, even if I write the lines as 00 input, 01 this, 01 that, starts at exactly register 100. That's what the base register talks about. So it gives the computer a bottom line. Is that clear? Those who ask, like, I'm coming onto the physical address, but do you understand the work of the base register now?
Yes.
So it sets a bottom line for the computer to always not go beneath, so that it will not have it clashing with already held storage spaces. So the base register sets a bottom line from where execution starts. Keep that in mind. That's the base register. So this means the computer will always start execution from the base register that you set. So let's say we set our base register to be 49 over here. What this means is, if I decide to execute the instruction on line, this is line 2, right? Line 02. If I am executing, that's a regional hasaya. Program counter is going to hold the value 02. Is that not right? Because it means it is holding the instruction for the next register, which is 02. But because the instruction or the base register says we are starting from register 49, it is not going to read the instruction address. It's not going to read the register as 02, but instead it's going to read it as 2 registers ahead of 49. So we are, the bottom line is 49, is our starting point, not 0. The physical address we are actually going to hold the data on is going to be the value of the program counter, which is 02, plus our starting point, which is 49. So what will the physical address be in this instance? Who can tell me that? You can share, and just unmute and share if you know.
Come again.
I was saying that according to what we know, the bottom line is the base register, which tells the computer to not start execution on before a particular region. So now let's assume we have set our base register to be 50. It means every instruction will be executed only after 50, right? Now, if I am standing on the instruction here, the program counter is going to hold the value 02, telling me that, okay, then what we are going to do is, I'm going to start from, I'm going to move to instruction 2 here. Now, normally it should be read inside the register that we are starting at this very region here, where the instruction 2 is. However, because we set the base register to be 50, the computer is rather going to start execution from number 50. So this means even if I am on line 2, when I'm supposed to be focused on register 2, the computer will start execution from 2 registers after the bottom line, which is 50. So when that value is called the physical address, we start at 50. That's the base register. The program counter says, go to register 2. It starts at 50 and continues 51 and goes to 52. 52 now becomes the physical address. So the logical address is already given here. That is 02. But the physical address starts at the base register and continues to where the logical address is supposed to be held, according to the program counter. So in order to know what the physical address is, you always combine the starting point, which is the base register, with the instructions exact logical address, which is the program counter. Combining that is what gives you the physical address. Is that clearer now? I hope it is.
Yeah, yes, sir.
Yeah. And
Yes,
then when we
it's
are doing
okay.
it in the when you are doing it in the simulator, you will see it even clearer. So remember, the base register tells the computer that always starts at this point. The logical address tells the computer that each instruction is line 1, this is line 2, this is line 3, this is line 4. The program counter holds the number of the next instruction. Since we are starting at register 100, in this case, it says the register is 100 for the base. Since we are starting at 100, when the program counter says go to instruction 2, the physical address will now become 102. It means it's going to start execution from register number 102. So we get the physical address by combining the base register with the logical address. So it says, example, the program starts at 100 according to the base register 100. An instruction at logical address 2 will be found at physical address 102, which means we have added the starting point, which is 100, to the region where the instruction is being held, which is 2 boxes away from 100, so 102. This lets programs move in memory without code changes. Let's keep that in mind. Now, instruction categories, we will need this to as we run our CPUOS simulator. There is a data transfer. These are functions or instructions that are used to move data, like load word that you see a LDW, or store word, or move. So load word will load data that has already been stored. Store a word will now store a data that has been given to the computer. Move carries data from one point to another. So it copies the data, sends it to another region. That's what it is. Then we have the arithmetic, where we do our additions and our subtractions and etc. etc. These things always have an influence on the status register. So I mentioned earlier, if you do a subtraction or an addition, you can get a negative number. Then the status register will flag it as an N. If you do an addition is bigger than the storage space, the status register will update it and say, okay, this is an overflow OV. So remember, arithmetic, we'll use this later. Data transfer for movement of data, like loading, storing, moving, and arithmetic for performing mathematical operations. And we have the stack operations. The stack operations are what take data and now forcibly store them in memory. So pushing means we are adding to memory. Popping means we are removing from memory. The stack pointer is the one that changes. So the stack pointer will only change when we add instructions that will push on the stack. So remember, we are talking about a lot of storage spaces. So we're talking about registers, and we have talked about the RAM, and we are saying the stack is a separate RAM that is used to hold either high-level register data, or it is used to hold explicitly mentioned data by the user. So the user says, store it here in the stack, then it stores it there. So you are going to see that in our normal operations, the stack will never update. The SP, it will never update. It will only update when we later come back and then we give it push or pop operations. That's the only time it works there. There are other ones like return operations too. They also affect the stack. We also have the control transfer. They change the flow of execution. Examples include the jump command. So they tell the operation how it's supposed to flow. The call command, the return command. And there is the halt command. It's for controlling the flow of the program. Jump Z. So jump if it's 0. These ones tell the computer how to control itself. Move from here to this side because this is happening. They can be used to set conditions as well. So now we are going to do a simple lab right now, okay? So everybody, the lab you've been waiting for, it is here. We are going to start inside our program. So let's look at exactly what it says. It says, create a program named demo1 and set the base address to 100. We are going to input data later. We are going to calculate something and then we get an output. So let's just get right into it, okay? So everyone, open your little man computer interface. It's about to get wild. So if you
I beg
have
you,
any
I beg you, please. Are we using
Central
little man
Processing
computer?
Unit OS, CPU OS, sorry. Mr. Joshua,
Yes,
CPU
sir.
OS, why?
Hello, Prince.
Yes, sir.
Please, this session is it being recorded or what? Because some of
Yes,
us we are not with our laptop,
don't worry, it's being recorded.
and so please, when we are done with the class, you can send it to this platform so that when we go home, then we can also practice.
The recordings are always made available in time. They are always made available in time. So tomorrow or today, possibly, they will be made available. We have put links to our platforms around. So don't worry, if you have the link to the YouTube channel, we always update you when the videos are uploaded. So stay with us. Okay.
Okay, all right, thank you. Because some of us
No,
we are not with our system, so
there is no problem there. We understand the situation. So, all
all right.
right. Yeah. So now we are going to add a program. Before I do that, let me clear my program from here so that so come to this region where it says program name down here, bottom down here. Let me see if I can use a pointer so that you can see clearly what I'm talking about. I just remembered if I start doing this, you guys will start talking about annotations, notifications on your screen. No, I'm using my mouse. Follow my mouse. Come to this region where it says new program, program name, under programs. So if you have not selected program, select program here. Have we all done that? If you have done that, where it says program name, just enter a program name. So since it's our first start, let's write try one. The one as our program name. And then we set a base address. Remember what the base address is? It tells the computer where it should always start the execution from. Do not forget that. So then our base address that I'm going to set, you can set anyone, but let's use 100 just as was in the slides I was using. So 100. Keep the pages number as 1 and then hit add here. Okay. So if you do that, you should see and that it has been updated. Where it says program list, your program has now been added there. Try one. It has now been added. If your base register is ticked here, Mr. Joshua Anand, yes?
Sir, please, my PC has been set to 0.
Yes, we are not at the PC yet. We have not
Okay.
written any. Relax. We have not written any instruction yet. So yes, naturally the PC will be at 0. And even if there was an instruction, if execution has not started, PC will always hold the next instruction to be executed. So if you have not started, it will still be holding 0. So don't worry, I see. Just focus on what I'm telling you to do for now. Go to where it says program name, add a program name. Use any program name you want, but just use try one or demo one. And then enter your base address. Enter a base address, a big one, 100, 200, whatever. And after doing that, click add. Clicking add will make it a program. It will come into your program list right here. And after it comes in your program list, I want you to ensure that the place where it says base address under your program list, right? Ensure that the box next to it is not ticked. If it is ticked, untick it, and then write the base address that you set over there. So you see this region here that I am. If this box here is ticked, untick it like this. And then inside the space next to it, type the base address you entered over here, type it into it at this side. So then we are using 100. Type it nicely. And then you can choose to just go ahead and then use this, but save it so that you can use it later. So we save. So everybody hit save and then store it on your device. So store it is try one. It is save. So then once you do that, you notice in this region here, in the center here where it says program list, it shows you the name of the program that you use. That's try one. It tells you that the base, which is the starting point or the starting register, it's ready now. I hope they don't turn off the lights. If they do, my laptop will go off in about 30 minutes or something. All right. So as I said, the base you have set is now 100. Telling the question and the what do we call it? The program that always starts execution from 100. And then it starts at the point 00. And then it tells the type of storage you have done right now. This is what we are using registers. Okay, we are going to, when we do our running, now you're going to see or appreciate what I was saying earlier more about how the base register works by operating with the program counter. Good. So now that we have set the program, let's move on to the instructions we use for the program. Now, unlike the Little Man computer where we could directly type instructions, the central processing unit OS simulator only lets you add instructions from the computer, a pre-made instructions, sorry. It only allows you to add pre-made instructions so that you, the user, knows that the computer, the processor, is retrieving instructions from storage. It is not typing instructions, but rather it is retrieving. So if it takes a user's data, it converts that into a code it will understand, and it matches that to an instruction it has stored, and then it executes that instruction. So they want you to have the feel of how the computer works. So in order for you to use an instruction, you will have to retrieve an instruction from storage. Is that clear? So where your program is, go to the next tab. It says instructions. Click on it. And when you click instructions, click add new. So let's add some instructions to our program. I want you to take your instructions pane away from this region right here so that you can easily see what you are doing. All right. So we are going to do some simple things, okay? Let's start with a simple instruction that moves data. Is that clear? Let's start with a simple instruction that moves data. Remember, movements of data means we are transferring data, right? You see, there are a lot of tabs when you come here. There is data transfer. It holds different types of opcodes, as you can see. There is arithmetic, and we mentioned that earlier. It holds different types of opcodes. There is control transfer. It holds different types of opcodes. There is comparison, and there is also input and output. We are going to start with the data transfer. We will not use input output because input output actually refer to your keyboards, your mice, etc., etc. The computer matches particular operand values to every device you are using. So for example, it recognizes a keyboard as 0. So if we are using input output here, we are just telling the computer that, oh, this is going to come from a keyboard. That's all we are telling the computer. It's not as if we are telling the computer that I am going to put a value there because it will not take any value from you. When you fix a value here, the value corresponds to a particular device. That's if you are using input output. That's the I/O you see over here. So we are not going to use that yet. By default, if it is set to 0, just leave it at that. It just means that we take input from a keyboard. That's what the 0 means. Then let's go to data transfer. So I said I want us to use a move command, right? So let's take move. What we are going to do is we are going to move a particular value to a particular memory address or a particular register. So let's take a random value. Let's type in a value like, let's say 7. So we are moving. Come to where it says value here. Okay. So we are moving the value 7. And come down to the second region where it says destination operand. So this is our starting point. And then this is going to be where we are going to end with this simple single instruction we are adding. So it says we have the value 7. We are holding it as our source. And now let's take it to the destination. Let's send it, come to where it says register. Make sure your register is ticked. And let's store it in one of the registers. Let's store that value in line, something like register 0. What this means is that take the value 7, store it in register 0. As simple as that. So everyone, have you done that? Respond with your mic so that I can tell.
Yes,
Okay,
sir.
because all right,
Yes,
good. So then after doing this, hit new. Yes? Yeah, please, there is someone trying to talk to us. Who is this?
Started by my network. Please, can
So I'm sorry, I can't really hear you. I feel like you're going through what I was going through yesterday.
I think his
But,
network is not stable. So
oh, so don't worry, we will upload the video so you can follow closely later. But for now, we move with
So
time.
yeah, Prince, can
Yeah,
you do it after the class? Then you send it to the group because some of us we like because of our work, so we reach home
please,
late.
who is speaking right now?
Yeah, this is Frank.
Okay, so I believe you are the same one who was, and I mentioned that I will do it, right?
Yeah.
Okay,
Okay.
so
All right.
yes, I have already answered that, so I'll do it. Yes, we deal with time. It's time we deal with. So let's finish this with time so that we can do the uploads later with time. So back to it. So now after you have added your value and the register, remember what this means. The source operand means we are starting with this particular value here. Here, 7. That's what we are telling the computer. And then since we are using the move instruction, it says move the value 7 to register the destination. Destination means where we are stopping, right? So it says move the value 7 to register 0. So take it and store it in the register 0. So hit new instruction when you're done. And you realize that it will be recorded as an instruction in memory. So it says your physical address is given as 100. Your logical address is given as 0. And it says you move data value 7 to register 0. It also tells us what the base is, and it tells us the time that it has spent. Now, I want you to follow this closely. See what the physical address is and see what the logical address is. By logic, this is our initial line, right? So it is line 0. That is correct. But because we are aware that we have told the computer to start at the base 100, it will start execution from that side. So then this means that every process it does, if it takes data from storage number 5 and then adds it to data from in storage number 7, it is going to come and do every other operation on it and display them after register number 100. So then the physical address is currently 100, implying that the program counter is now on 0, and 0 plus 100 is what? 100. Let's add a second instruction. So currently we have moved the data value 7 to register 0. Keep that in mind. Let's move another data value. Let's move data value 5 this time. And let's move it to register 1. That's a simple one to do, right? So take your data value in the source operand, data value 5, move it to register 01. And when you're done, hit new instruction so that it adds here. So that you can see the first instruction was held here. The computer has jammed to 106. So it says this time they are using the intervals of 6 to store the data. In other words, 7. So from 0, 1, 2, 3, 4, 5, 6, 7, it comes all the way to the next instruction here. This very line. So you'll see that the next one will also be an increment of 7 starting from 6. So it uses this to store data in a particular sequence so that they do not get mixed up unnecessarily. So now we have register 1, we have data value 7 in register 0, we have data value 5 in register 1. Now let's add these two inputs, shall we? So where do we do our addition? Should it be at arithmetic, control, comparison? Which one should it be?
Arithmetic.
Arithmetic. Thank you.
Arithmetic.
Very good. Very good. So you come to where it says arithmetic, and then you are going to use add. So choose the arithmetic operation add since you are trying to add the two data values. So then we are going to add register 0, right, to register 1. So don't come to value, rather come to register. So we are adding what is inside register 0. It's already written here, but if it's not written there, just choose register 0. We are adding what is stored inside register 0. And you come and then you choose add it to register 1. And you realize that it says register 1 is a destination, right? It means after it does the addition, it is going to store it. So it combines the value in register 0 with the value in register 1, and it still holds the answer in register 1. So register 1 gets updated. Keep that in mind. So then we have new instruction. So we add that, right? So you can realize the pattern. It started from 0. It goes to 6. It goes to 12. Definite increments. A sequence. Let's proceed. Now that we have that, remember, you always need your halt program, right? The halt sense so that the computer does not run endlessly and then it stops. So which one do you think we should use? Should we use data transfer for the halt, arithmetic, control transfer, or comparison? For halting, where do you think we'll find it? Should it be in data transfer, arithmetic, control, or comparison? Remember, input-output just points to hardware devices. You said control. Yes, that's right, control. Control. Good. So if you come to control on the bottom down here, that is it, the halt instruction. So for the halt instruction, you don't need to give it a value or a register or whatever. It just halts immediately. So once you click halt, you just hit new instruction and it is added here. So now what do we have? We have an instruction to move data value 7 to register 0, an instruction to move data value 5 to register 1. We have an instruction to add what is in register 0 to register 1 and store it in register 1. And finally, we have an instruction to halt. So close your instructions. Close it. Let it go away. Now I want you to follow closely and you are going to see what happens here. So I was previously running an instructions in my program. So you may be seeing some parameters here. For example, you can see instruction register here, memory address, blah, blah, blah. But it should get updated if I do my running. But yours should be different. So everyone, tell me, what does your instruction register currently say? IR. Where it says IR, what does it currently say?
Empty.
It's empty, right? What does it say as MAR? Empty. What does it say as MDR? Empty. And what does it say as base register? BR? Hello?
100.
100. So what this means is that your base register has been set. And you realize what this SP is. So we said is the stack pointer, right? It points to the values that you'll be storing down here, this region here called the program stack. And the stack is a separate RAM, or it's a separate part of the RAM that holds data that are either high level or have been explicitly told, have been explicitly directed by the user to hold in that very region. Okay, the status register will be taking notes of overflows or zeros or negatives. Okay, keep that in mind. Now let's proceed. We are going to run our instruction one by one. This region where it says pipeline also has its use. It just basically runs several instructions at a time, but we are not there yet, so let's forget pipeline. Let's focus on the basis. Come to this region here. Come down here where it says program control here, and then hit step. We know what step does, right? I mentioned it in our lesson. What does step do? It executes the instruction line by line. So click it just once, hit step, and tell me exactly what you see. Everybody click step. I won't click. You click step, and you share what happened to me. So let me see. Raise hands and then share. So click step. Yes, Mr. Joshua Annan. What happened when you clicked step for the first time?
So I see CPU 0 runtime 00 colon 54 colon 15.842.
All right, Joshua, God bless you. But that's not what you're looking at. Go to the program counter PC. What does it say?
18.
Your PC says what?
18.
Wow. Okay. Joshua says his PC says 18. All right. Is there any other person who has run it? So Joshua has his PC saying 18. Yes, Auntie Monica, what does your PC value? What's your PC value?
Mine is saying 17.
Why
Yours
is it
is saying
really there?
17. Did you hit run
Yes.
or you
No, it's
hit
not really
step?
an place.
Mona, did you hit run or you hit step?
I hit step.
Okay. Yes. Any other person who has run the program? All right. So now let's see what is happening here. So when we hit step here, we are telling the computer that stand on this region. I hope, wait, so Mona, you see the red arrow on this, was it pointing to this region here?
Yes, yes.
Oh, no. So then what you have done is you run this very line.
What do you
So
say?
that is why it says 17. It has registered
Where do you
the
say?
instruction of that line inside the program counter.
It is really
So I
not
want you
very
to, everybody go back to your, Joshua, everybody, go back to your program, hit reset program, come to this region where it says program control. And this is why it's important to reset. That forces the program to always start from the first line, 0, 100, 100, 0, 100, okay? So everybody hit reset program so that it goes back to the first line. Have you done that?
Yes, sir.
Now I want you to step again, and then let's see what happens. So if you step, after resetting and stepping, Mona, if you have done that, share what your new PC value was.
It says 6.
It says 6. And what does the program counter do? Remind me of what the program counter does. Someone remind me of what the program counter does.
It holds the next
It holds the memory
instruction
address
to
of
be
the
executed.
instruction.
Good. So it holds the address of the next instruction to be executed. So what this means is that your program counter it knows that we have now done this line. So it's holding the address of the next instruction. That's the logical address 6. That's what the program counter holds right here. So now I'm also going to run my program as you have done. So I reset it and I hit step. So when I do that, my program counter is now at 6. It's here. Now, what does the instruction register say? It says move data value 7 to register 0. So then inside the instruction register, currently we are holding this very instruction here. So you see the instruction register takes the instruction that we just ran. That's the instruction up here. It moves that data value all the way here. So it tells it this. So it says we are targeting which memory address. So the memory address register is starting at which memory? It says 100. So as I mentioned earlier, execution is not starting from 0 as you see here in the logical address, but rather it is starting from address 100 inside your RAM. And then the memory data register follows exactly what the instruction has given. It says, okay, so now we have taken the data value 7 and we have stored it inside register 0. So the memory data register or the memory buffer register, it takes the data value and does according to what the movement said. So the address gave us where to start from. And then the memory data register has told us what we have done with the data. So currently we have moved data value 7. We are holding that inside register 0. Keep that in mind. All right, that's good. So let me reset this. We run the first time. We got, I just ran everything. Let's reset. So Mr. Joshua, when you hit the thing, you said it mentioned runtime, etc., etc. It means you didn't step it. You run it. I've caught you.
And
I
I
told
had
you
6.
to. You had 6. Okay.
Yeah.
Good. So now you had 6. That means you stepped it. So now, after stepping the first one, let's step the second one again. So when you step the second one, I want you to take notes, okay? Everybody reset your program again. There is one thing I want you to take notes of in the register column. Tell me the differences you can see happening, okay? So reset your program, hit step. Now, go to the register column and tell me what you see. What we did was move value 7 to register 0. What do you see in register 0? Do you see value 7? Then it means you have succeeded. So on this region where the R00, R01, etc. are, do you see R7? Just give a thumbs up or respond with your mic. Good.
Yes.
All right. So then this means we have moved data value 7 successfully into register 0. Let's run the program. Let's step it again. If we step it a second time, what does it say? It says now we move data value 5 to register 1. So we have moved data value 5 to register 1. So as you can see, 7 is held in 0, 5 is held in 1. So if we run the third line, what will happen? It will add register 0 to register 1. So let's run. And then you realize the program counter, you see how it changes? Now it is holding the address of the next instruction, which is 12 over here. So if I run it again, let's do the step, sorry. If I step it again, what happens is that the address R00 is now combined with R01 and it is stored in register 1 since we chose that as the destination register. So when you add your 7 to 5, you get 12. And if you come to register 1, what do you see there? It says 12. So the reason why you were finding it complicated to run your instructions with this, unlike the little man, is that over here you just have to add your instructions from memory explicitly. But over there you could just type the instructions and then you run. That's the only difference. So now we see that it's added the value 7 to the value 5 and it has stored the answer in register 12. And finally, if we run again, if we step again, the program halts. So when we halt, it says central processing unit runtime, blah, blah, blah. It tells you the time, how long the program spends on catering for your instructions. So ladies and gentlemen, this is basically what or how the little man computer functions. Let's not be in a hurry because there are more instructions we can look at. Okay. Yes, Mr. AP Abwaje Prince. Yes. Mr. Abwaje, I don't think you are speaking, or I can't hear you. And please, can you hear him talking or?
No, we can't hear.
Okay. Boso Abwaje, please, we cannot hear you speak, so do something about your mic and then we proceed. You may drop your question in the chat. Maybe someone can read it for us, okay? Okay. Now, what we have done basically now is just moving data from one data storage value to another and then combining them. Remember, input outputs do not work the way you think. They refer to devices. They are like channels telling the computer that the input or the user's input is going to come from their keyboard, is going to come from their mouse, is going to come from their this, is going to come from that. Each single value there refers to a particular device. 0 refers to keyboard, and so on and so forth. So we do not use input output to do what we're doing in Little Man Computer. It's unrealistic because you will have to tie your input devices to the CPU so that it knows that when someone hits this, it's coming from the keyboard. And that's where the I/O comes in. Now, let's try some storage, shall we? So we are going to add another instruction. We cannot add the instruction after halt, else it means the program will run and stop and then it will start again. So let's add another instruction. Let's store the value that we got inside a different memory space, okay? So we are going to choose a different memory space. I want you to do that yourself. I'll show you which one is for storage. So everybody follow this, store this value, the answer we got in register R01. Store it inside the memory space. I'm going to allow you to do it yourself first and see if you succeed. And then when we are done, we all try it together. Is that clear? So remember how we added instructions. Currently, I'm trying to add an instruction on top of HLT. So you come to where it says instructions down here. It's quite stressful, but just do it anyway. And then it says, we have instructions here. So here you can read, right? It says insert above. It means you are going to insert an instruction on top of this line here. So insert above. So what are we inserting above it? I said we are going to store. So then the storage instruction, is it data transfer or is control transfer? It is data transfer. So then go to this side where it says store word, STW, hit that. So we are going to store something. So go to this side where it says store word. And after doing that, I want you to use your computer or your interface, your CPU or simulator interface, following these things right here. Store the value in register 01, right? Store it in a new register. Store it in R20. Everybody attempt that. Send the storage of your answer. So we go to insert above on top of your HLT. And when you are done doing that, go to data transfer, choose STW for storage. So you store the words that have been kept in your register. You store it inside the new register 20. Who has successfully done that? I know some of you here, you work quite fast. All right, Mr. Abuaje Prince, if you have successfully done that, right? Should I allow you to share your screen or you're just going to run us through it? I think you should share your screen. Mr. Abuaje, please go ahead and share your screen. Okay. Where is he? Abuaje, why? Good, Abuaje Prince. Yes, Auntie Monica. Yes, Madam Monica, your hand was up. All right. Mr. Prince Abuaje, let me allow you to share your screen. Where is he? Where is he? Has he left the meeting? Wow. Fast. If there is anyone else who is willing to share, or if you won't share your screen, at least tell us what you have seen after entering those parameters. Tell us what you did. Okay. No one is willing to talk. Okay, let's proceed. Let's pay attention. So I selected insert above. It means I want to add an instruction on top of this very line. The arrow points to the current line always, okay? And then we are going to use a store function. So we go to where it says data transfer storage. You store it down there. We are not storing the data value. Rather, we are trying to store the contents of a register, which is R01. So I store the value of R01. I go, that's the source operand. I take this from that source and I store it in a new register. So I can store that in maybe register 20. That's what I asked to do, right? Good. And then I do insert instruction. So it is here. It says you store the value that was stored here inside this region right here. Let's keep that in mind. So it says store blah 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 blah. And then we try the running again, and then we see what happens. So then just reset your program, step, 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 step. So what this means is that it is storing that in the register 20. Now, then you step again and it halts, or you run, or it goes all the way through to the bottom. Now let's look at more instructions that we can add to this thing, okay? Before we proceed, if you have any questions, please make sure to ask, okay? Let's see some more instructions and how they work. And then for the rest of it, I'll allow you to play around with it in your own time. All right, so yeah, Awaje Prince. So you said you were trying to talk, but we can't hear you. So I was saying, enter your query in the chat, and we can read it. So currently, I have my chat open, so you can go ahead and enter your query, or you can attempt talking again. Maybe it just might work. Ah, yeah, 25th December. All right. So you know something, Awaje, if you are ready, just raise your hand, and then I'll read what you said in the chat. Good. So everyone, keep these instructions in mind. Now, I want us to do the same thing that we just did, but this time, let's try using subtraction instead. Give your computer different data values and then do subtraction. Someone should share their screen and then walk us through this process. Who is here? Is this Mr. Joshua? Okay, Mr. Joshua, Mr. Jed, Auntie Vida, Auntie Monica, Mr. Joel, Madam Oponwa, Emmanuel, Mr. Joshua Champon, Mariam, Rabna, Bernard, Ajekum Frank, Prince. If any of you has their screen ready to go, they may share. Auntie Vida, are you ready for us?
If I'm having light out, so I'm only watching.
Okay.
I'm only following. That's why I'm not talking.
No problem. Yes, so yes, Mr. Awaje. Try unmuting and speaking and let me see. Mr. Awaje, unmute and speak
Hello,
and let me see.
hello,
Yeah,
hello,
I can hear you.
friends.
Okay,
This is
Ajekum,
Frank.
yeah,
I'm using
yeah.
my phone, also I can't share my screen. I'm
Okay, no
using my phone to
problem.
join.
No problem, brother. I understand. Mr. Abuaje, what about you?
Can you hear me? Hello.
Yeah, I can hear you now.
Okay. Yes. Thank you. So, is that what should I do?
Yeah, I was asking, you can share your screen. Initially, you wanted to ask a question, but I was saying that you can
Yes,
type it in the chat
I'm
bar.
unable to share my screen. I don't know what you've done, but then I get that circle
Mr.
with the.
Mr. Joshua, can you add him as a presenter? Just
Okay, sir. Okay, sir.
yeah, just click his In the list, just click his name and then add him as a presenter. Let me see something. That's Mr. Abuaje Prince, right? Or Ajekum Frank Prince.
So, Mr. Prince,
Okay, so you can go
you
ahead.
have to stop sharing.
Sorry, Vida, what did you say?
I said you have to stop sharing so that he can share.
All right, okay. So, Mr. Abuaje, you have what do you call it? Joshua has allowed you as a presenter, so you can go ahead and present now.
I should share my screen.
Yes, please share your screen. So I hope, if anything, at least I have made the setup clearer to you, and then I have eliminated or at least erased some of your confusions from your earlier lessons. If I haven't done this, then I think it's juju at this point. Wow, is that where you went to put your store command? I beg you, raise it. You are storing at the top. So, Mr. Abuaje Prince, you know something? Go all the way to the top of your setup at the top there, right? And then, yes, good. Select good. Now that you're there, come down to delete down here. Or you may move it down, but you come down to delete. Delete it. Come here. Go down here. Go to where it says delete. At your instructions column, go down, down, down. Where there is add new, it says above, go and then click delete so that it goes away. Good, yeah. Good. Because what you have done is you have put the storage instruction before the codes were even executed. That's right. So now wait, hold up on the insertion, okay? Hold up on the insertion. I want us to start a new program. Okay. So first off, clear. So hit delete, or you can go to the top, hit delete, and then it deletes, and then you hit enter repeatedly. Good. Yes. So delete, enter. Just press enter so that you don't have to go back and forth with your mouse. Enter. Okay. Delete. Did you hit load? All right, good. Let's add new. So I'll go to add new. Add new, yeah. So now I want you to add an instruction that will load data. So let's use movement. So let's move data. So move a data value. Let's take 10 to register 5. Oh, okay, mastery. That's good. That's good. Good. Now let's move another data value. This time, let's move a value like let's say 17. 17. Let's move it to register 12. Move it to register 12. Good. Add that. Now, add a subtraction command.
I should do what? I should do what?
Subtract. So sub, S-U-B.
Okay, so I should subtract what from what?
So okay. So we are going to subtract the value that is being held in 17 from 10. So you do RO5 and 17. So subtract RO5 and 17. RO5 and 12, sorry. So RO5. No, the initial one was, wait, Mr. Wait, read your instructions. You see that it says move #10. #10 is the constant, the number. It says move that to register 5. So the register for the initial one is 5. So if you come to this point where you have register inside your instruction, good. So you 5, good. And then we are doing that's 5 minus what is stored in register 12. Excellent, very good. And now we hit new instruction to add that. Good. Good. Now let's add the halt command here. Right. This guy understands. You understand your thing. Good. So you're there. So now close that. Go to reset program so that it goes back to the first line. No, yeah, no. Under program control. Under program control. Under program, yes, good. There, that's it. Click. Good. Now that you have done it, let's run them step by step. Don't run, step it. Good. So one, everybody follow. I want you to follow closely so we can see the usual stuff. Okay. It has stored, look at its register value 5. And register number 5 has value 10. Step it again. All right. So when he stepped this, register 12 has value 17. Step it again. Now everybody pay attention here. So then when you step this again, what did we have? Where do we go? Where do we go? Where's your answer? Your answer is stored in register 12, and then it is what? 7. So then what it has done is it has done the value that was stored in 17 minus that. So 12 minus, what do we call it? 17 minus 10, and it gives you 7, stores it in register 12. So the destination register is always your storage point, okay? So now, I want you to edit your instructions a little. So let's go to edit. Come back here. Take your line, your what do we call it? Bring your mouse to where your instructions are. Click on the movement instruction, the very first movement instruction. Click on it. Go up to where your lines of instructions are up here. So good. Yeah, that one. So click on that instruction. Good. Now come to edit. Click it. So edit allows you to edit your previously added instructions. If those status bubbles that keep popping up are confusing you, you can just use Control plus F12 to stop them from interfering. All right. So now we are going to change the value that you have. Change it. Yeah, change the value that you have from 10 here. Now change that to 17. So let's swap the place of the values and see what happens. So just change the value to 17. So edit instruction, and then it goes. Boom. Do same for the second instruction, the 0106. Yeah, edit it. So everyone, I hope you are following. This is how you edit your previous instructions. Change that to 10. Good. Edit. Now reset the program, and then let's step it again. So step. Now, what do you see at where the status flags are? Something has happened. What do you notice there? It has flagged negative, right? And it assigns it a particular number in the status register too. So then it means the status register indeed recognizes negatives and zeros and etc. So if we had done 10 minus 10, we would have recorded a 0, etc., etc. The values you are seeing inside the value you are seeing in your status register up there, each one goes for a particular different type of, what do we call it, status. Okay, so I want you to keep those parameters in mind. But just know that the status register flags the states of your arithmetic inputs. Keep that in mind. Now let's move on. We mentioned the stack, and currently you can see the SP. So Prince, keep sharing your screen, okay? Everyone, you can see the SP here where it says 8096. That stack right there, it has not changed despite how many times we kept running our program and running our program. It just stays the same. And this means one thing. We have not touched the RAM stack. So you see, it says the central processing unit instructions, top left corner on his page. It is also giving us what? RAM. So it says central processing unit instructions in memory, RAM. The stack is also in RAM. So how is it that we are working RAM, and yet we are not affecting RAM? This means stack is a separate RAM on its own. Now, we are going to now store a value inside the stack register. Before we do that, let me explain how the stack works to you. Oh, I think I already did that, but I want to explain with a demonstration. But first off, let's run the program so that Prince, you share the running and everything, and then I explain later after we are done. So go back to add instruction. They don't use add, use insert above so that we can insert it above halt. Good. So now when you go to your insert above, we are going to look for push. No, push is a data transfer. Good. So push PSH. Yes, push. Remember what we said push is about. If you push, you are adding to the stack. So let's push. So if we push, what happens is the stack is going to grow higher, right? So then the value is going to increase. So then it's like a basket. And then you are adding clothes to it. If the bottom was 0, when you put one cloth into it, it goes to level 1. You put another cloth on it, it goes to level 2. You put another cloth on it, it goes to level 3. What? Yeah, not today. Ah, oh no. Yeah, hello. Sorry. My network broke off. Sorry. I'm back in. Okay. So we are going to add the push instructions. So as I was saying, yeah, hello. Yeah, well, the network, sorry. So as I said earlier, the push is a command that helps us add to the stack. And then you can see the stack. Keep that in mind. Now there are different types of stacks. We have, wait, so everyone, please hold on. Guys, I see what the problem is. Please hold on a second. Let me stop this quickly, else my network, I will have the same problem. Yeah, hello everyone. Sorry, I'm back. All right. So back to what we were discussing. As I was saying, the push operation, you have a basket. The base of the basket is 0. You put a cloth into it. It goes a little higher. So you see that as level 1. You put another on it, it goes higher, level 2. So it means your stack pointer will always be pointing to the top of the basket. Therefore, the value keeps incrementing to what is at the top, depending on the size of the cloth. If I put a cloth that will cover 3 levels at once, the stack pointer will move from level 2 all the way to level 5 because the cloth has covered 3 levels. If I put another cloth on it, it covers 2 levels at once, it will jump from 5 to 7. So then as you keep stacking, the value increases. There are different types of stacks. We have some stacks that grow upward and stacks that grow downward. In stacks that grow downward, the more you add, the smaller the stack pointer value is. What this means is the lowest part of the stack is going to be seen as the deepest part of it. Therefore, that's going to be the highest region. So when we are at the bottom, we'll be at maybe 1,000. When you increment the stack with something, we come higher. It means we are closer to the surface this time. So it will drop from 1,000 to 999. If you add to it, it keeps dropping. So we have stacks that grow upward. Stacks that grow upward, when you add to them or when you push, the values become bigger. And then we have stacks that go downward. When you push, the value becomes smaller. Keep that in mind. All right. So yes, add your push command. We are going to push what is stored in register. So go there, go to where it is pushing. Go to, yes, register. We are pushing what is stored in the final register. What was the final register we used? Guys, what was the final register?
12.
12. Excellent. So we're going to push what is stored in register 12, okay? And then if you do the pushing, because it is pushing into the stack, you don't even need to choose a destination because the stack always follows its own level. So it's a word. A word is 2 bytes, 2 bytes, right? So then normally, or in the normal sense, our stack should increase by 2 values. So hit insert instruction and let's see what happens when we do the stepping. Yeah, now close it. Excellent. So now reset your program and let's do the same thing from the start. So just do it one by one, step. And when you get to push, we see what happens. Yes. Good. Everybody pause right there. Come to this region where it says stack. You realize that something has happened here, right? It has TOS. It has post value 0. It has this, and even the stack pointer has increased from 8096 to 8092. And I remember I mentioned that a word is a byte size, is 2 bytes. That's 2 bytes, so it means it has increased by 2 bytes. You've combined that with it in a stack. So then that's what you're seeing here. And then there are some parameters here. It says TOS. TOS refers to the top of the stack. So we've added to it. And for that reason, it has become that. And then we have blah, blah, and blah, blah here. We can add another value to the stack and push it again. Okay, so you can go back to add instruction. So insert above, good. Yeah. This guy, you're fast. You're fast. You do our name justice. Principal. You know the joke. All right. So then what you're going to do is you're going to pick an instruction from here. Let's use the move instruction. So let's use move. So go to data transfer and then let's move. Top up there. So let's move a value like maybe 6. So move 6. And then store it in any of the, choose a register, a random register, choose one of your choice, and let's see. Choose something. Okay, 22 is good. And then insert that instruction. Have you done it? Good. Now we are going to push. So we are going to add a push command under this instruction again. So add another push command and let's see what happens. So this time we are pushing register 22 into the stack. So it means what you are doing now is, now you are not just storing them in the memory, you are storing them inside the stack memory. And they can be retrieved later. And you realize that the only instructions that are affecting this currently are the push instruction. Good. All right, this guy is fast. We are pushing register 22. Excellent. Insert instruction. Good. So now close and come reset the program. This time just run it. So reset it and run it so that it goes all the way through. And then we can just see how the stack increments. So run. So you see, as it followed, it moved from 896. Now it has moved to 800,000. It means we've added 2 words to it. Then it says that the top of the stack is 80026. Sorry, the top of the stack is the value with the address 6 and blah, blah, blah. And then it says the bottom of the stack is this side here. And it's always pointing to the top of the stack. And that value are the number of that particular stack address is here. That's 8,100. That's the top of the stack. Always points to the top. So not the bottom. So as you can see, it is gray. It has grayed out the ash parts showing you that's the stack. Now, if you want to take out of the stack, what you do is popping. So popping is when you remove from the stack. So let's remove something from the stack. So we are going back to our instruction. This time you pop one of the values in the stack. So pop something from the stack. So you can do pop. So he says above. It's a data transfer. Something. Yeah. So just pop the same register. Let's use register 22. Yeah. Insert instruction. Insert, good. And then run it. So reset the program and then run it. So now study what has happened. What we pushed, the second value we pushed, that was 22, has now been taken outside of the register, implying that it has been popped a year frame. So therefore, the stack pointer now points to the top. And then the top is no more at 1,000 again, or 100. It is no more at 8100. Because we have reduced the stack, it has dropped to a lower level. So now it's on 8098. So then the new top is now 8098. So then that's the job of the stack pointer. It always points to the top. Okay. So I think at this juncture, I have addressed all the points of the lesson, at least this first lesson. I've addressed all the points of it. And this is introduction to the Central Processing Unit Operating System Simulator. So if you have noticed, it is not about writing codes. It is not about writing codes, but it is more about looking at how the simulator works. So even in the little known computer, we got a chance to fool around with codes. But over here, you see, everything you do, you have to be able to follow it with every single thing that happens here. The next time we meet, we'll see if there are new instructions that we have to look at. And then if we are done with this, we can move on to the main slides. And as time goes on, with every single practical that we need to do, we'll also address it here. Let me just say that you have been a wonderful audience. I don't know if I should call you an audience or a class for today's session. And I believe the session has been very helpful. If you benefited from it, I'm glad you came, etc., etc. If you didn't benefit from it, don't worry. The video will be uploaded. You can